So I've given you some time to be ready with a pen and paper. Let's begin this discussion. Again, I'll begin from the very basics. We talk about, first of all, what are we doing today? We are talking about a reaction, a chemical reaction. Now, again, I'll repeat the fact that I understand these are very basic things that you've already done, but it is essential we understand it from the beginning itself so that we can build upon what we know. This way we will be on the same page here, or I hope we will be. So basically, what does chemical reactions talk about? It is nothing but transformation of matter. Remember, the first law of the thermodynamics states that the fact that matter can neither be created nor be destroyed. It can only be transformed from one form to another. So basically, we're talking about transformation of matter. Therefore, when we talk about chemical reaction, we first of all talk about reactants. Reactants are those chemical compounds, they could be molecules as well, or elements, they could be elements as well. Remember, please remember what the difference between these are. I've already explained them in the last class. So basically, chemical reactions talk about reactants combining together or reacting basically to form products. This is the basis or a very basic way of representing chemical reactions. One thing you should note is the arrow itself. Now I understand why is it a big deal. The arrow, I'm circling it with a different color. The arrow does not necessarily have to point in one direction. There is another concept, I think I introduced this in the last class as well, the concept of reversibility. Theoretically, all chemical reactions are reversible, but due to various considerations, particularly energy considerations, most reactions that you've come across till now are actually practically only in one direction, wherein reactants combine in various ways and they form products. That is the usual chemical reaction we go for. Now, however, across the various biochemical reactions that you witness, that you come across, you will notice that they are reversible reactions. What that means is that the reactants, in the same way that the reactants are forming a product, the opposite is also happening. The product can break down or disintegrate into the reactants as well. So when we talk about reversible reactions, we are not dealing with the amount. We are basically dealing with the concept of equilibrium, wherein the number of reactants combining to form products and the number of products disintegrating into the reactants, it is almost equal. So the disintegration of the products and the formation of the reactants, it is in a way at equilibrium. It means disintegration and formation is happening continuously. We reach what we call as an equilibrium. As I said, and I repeat, all across various biochemical reactions, you will notice the reversible equation mostly. That means a lot of the biochemical reactions, as I've said, theoretically all chemical reactions are reversible, but due to various considerations, we don't usually, especially in chemistry, you have not come across reversibility a lot. In biochemistry, we have almost all reactions as reversible. Now, while we're dealing with reactions, it is essential you understand that reactants combining to form a product, it can sometimes require energy, a lot of it. And living things, because we're talking about life, chemical reactions in the living system, there are limitations, there is limited energy that a living system can provide for this reaction. Therefore, energy that is required for the reactants to combine may not be met directly. I repeat, usually reactants require energy to combine together, especially if they're in this stable state. Usually reactants in the stable state are what we mention as they combine. But for this combination, for this reaction to occur, energy considerations are usually so high, these reactions cannot occur without a friend. This friend is called a catalyst, and usually you denote catalyst on the top of the arrow. On the top and bottom, you can mention the catalyst here as well, depends on how many catalysts exist. What is a catalyst? As I've said, it is a friend who will help in the chemical reaction, in the reactants combining, but the most important part is it itself does not participate in a reaction. That's a very important aspect. Catalysts are those chemicals that do not react themselves. They only help in changing or modifying the rate of reaction. Please realize the words and the terms I use. Please observe the words and the terms I use. There's a reason why I use them. They're supposed to be technically correct. Even though I'm trying to explain things to you, the words and terms I use are technically correct. That is why when I say that a catalyst can modify the rate of reaction, the modification does not mean in one direction. If it's a reversible reaction and a catalyst is helping it, then remember, it can help in the formation of product, it can help in the disintegration of the product as well. So when a catalyst modifies the rate of reaction, it could be either ways. Of course, in this chapter, we will deal with what we call as biocatalysts, which are enzymes and some properties of those enzymes. But the most important part you should understand is almost all biochemical reactions occur in the presence of these catalysts. Therefore, you should already know what a catalyst is. It is a friend that is helping in the change in the rate of reaction. If you take up this particular equation, it is helping in the formation of the products. It usually reduces the energy considerations of the reactant. Again, as I said, maybe not the catalyst part, but other things you're already aware of. If you understand the concept of chemical reactions and how they occur, then we should move further now and introduce you to the type of chemical reactions that exist. Now, even though you have studied the types of chemical reactions, and yes, according to chemistry, they are combination or combustion, disintegration, substitution, elimination, etc., etc. We are talking about types of biochemical reactions particularly, and here I will be dealing with the theoretical part. When dealing with the chemical reaction, you usually try to complete its valency. All the reactants should be you should complete their valency as well as the products as well. But as I said, I will be dealing with only the explanation part, the theoretical part of it, just so that I can introduce you to these topics. For example, if you talk about the types of biochemical reaction, the way I'm dealing with it, so this is not technically correct. I am warning you beforehand. This is just for the sake of understanding. One of the most important biochemical reactions that you can come across is oxidation. Oxidation, or you can simply denote it as addition of oxygen. This is literally what oxidation. Now again, as I said, chemically it means a lot of things. You can talk about oxidation in terms of transfer or release of electrons, because sometimes oxygen is not present in a reaction. It could still be an oxidation reaction. But as I said, for the sake of talking about biochemical reactions, we will only deal with oxidation being addition of oxygen. Wherever you notice a compound is being added, so whenever the reaction is plus O2. Now, of course, the other thing which is common in chemistry is to denote any reactant by R, any particular molecule by R. What this R refers to is X number of carbon atoms. I'll come to that as well. In the last class we talked about catenation. We'll proceed further with that as well. So let's say, for example, R is a chemical. It combines with oxygen. It forms RO2, let's say. This is a very rudimentary way or very basic way of writing it. Of course, you can come up with examples as well. I'll just show you another example. What I'm trying to tell you is, if oxygen is being added It can be considered oxidation. One of the most, and of course most of the time when you add oxygen, you're basically talking about combustion. Combustion reactions usually deal with oxygen being added, and oxygen being added means it being burnt. There is a phenomenon that we will deal with. In the last class, I introduced you to the topic of hydrocarbons. Hydrocarbons are compounds comprised completely of hydrogen and carbon only. Hydrocarbons, for example, the most basic hydrocarbon being CH4, methane. If you oxidize methane, ideally the products that you receive are carbon dioxide and water. Notice the word ideally. That is because it requires complete oxidation. If you have an amount of methane and you try to burn it, all of it won't be burnt completely. There will be something known as partial oxidation as well. So complete oxidation of, for example, methane usually yields two basic molecules which are called carbon dioxide and water, and this is true for all hydrocarbons. I repeat, all hydrocarbons technically they oxidize, and under complete oxidation they provide the products carbon dioxide and water. This is under complete oxidation. This is a very important aspect of organic chemistry, not only in terms of reactions, in terms of the understanding as well. Almost all fossil fuel that we receive, that we dig out from planet's earth crust, it is, all of it is nothing but variations of hydrocarbons, and when we burn it, ideally we are supposed to receive carbon dioxide and water. However, we've noticed that complete combustion does not occur all the time. For example, wood or coal. If you burn coal, ideally coal is various hydrocarbons that exist. Usually it is wood. Wood converts to coal, wood converted to coal during the Carboniferous era. But that coal that is being burnt, since it is not complete oxidation, it may end up giving us incomplete compounds as well, and those are hazardous. Not that carbon dioxide itself is not a questionable molecule that is being added. It's a compound or a gas that is being added to the Earth's atmosphere, but at least if we completely combust or oxidize hydrocarbons, we should receive these. We'll talk about oxidizing various hydrocarbons whenever required, but this is a general phenomenon you should be aware of, the fact that oxidation of hydrocarbons completely yields carbon dioxide and water. Similarly, we have the concept of reduction as well. Once again, when you talk about reduction and oxidation, you usually talk about electron transfer. But when we deal with reduction, in terms of organic chemistry, you can talk about it being addition of hydrogen. So whenever hydrogen is added, you can say it is being reduced. The substance is being reduced. And in fact, when you combine both of these, so this example that you notice, when you combine both of these, you get what is called as redox reactions. Redox reactions are very common in biochemistry. In organic chemistry, generally, you deal with a lot of redox reactions. Redox reactions are those reactions where both reduction and oxidation is happening. The same example that I showed you here, I'll write it once again. This is why I say you should attempt these with me. You should write them down with me so that you are aware of what is happening. If you notice, if you look at the carbon, and I'll mark it with a different color scheme. If you notice the carbon, oxygen is being added to it. So this is just for understanding. Remember, I will, wherever possible, if I'm not speaking technically, I will warn you beforehand. This is not technically the correct way. It is only for understanding. If you look at this, carbon is being oxygen is being added to carbon, we can say the carbon is being oxidized. Similarly, if you look at the other way, hydrogen is being added to oxygen, and you can say oxygen is being reduced. So this is a very typical example of redox reactions. There is a chapter where we discuss this redox reaction once again. It is the chapter of cellular respiration, where we will talk about glucose and its oxidation. Glucose is C6H12O6. Uh, if you remove, so in fact it is the same reaction as this. Uh, Instead of CH4, you can note down glucose. It's the same as above. Now, you should remember that these are not complete reactions. To complete these reactions, you need to complete their individual valencies as well. That is not what I'm interested in right now, because simply put, we are not dealing with the technical aspect of it. We're dealing with the theoretical aspect, that you should have a knowledge base ready for organic chemistry. So reduction and oxidation is one type of example of the kind of reactions we participate in. There are others as well. If you talk about hydrogen, if hydrogen molecule is added to any particular reactant, to any substance, it is called hydrogenation. Please understand the difference. You deal with hydrogenation. Once again, we will be dealing with it, particularly when you talk about, and this is true for our country because we utilize this product. When we talk about formation of ghee, it requires hydrogenation. Basically, what you're doing is, to go back to the concept here of reduction, you are reducing the product. You reduce the product to a state where it reaches complete saturation. Once again, I've introduced this in the previous class, the concept of complete saturation. Basically, your usual oils, they are double or triple bonds. They are double or triple bonds. When we talk about hydrogenation, we take these oils or any type of material which has these double or triple bonds, and we try and break these bonds, so that at the end of the day we get single bonded carbon. And once you receive this, it is supposed to be saturated. It is very difficult for these single bonds to be broken down. It requires a lot of energy. It is called saturated or saturation. I've already discussed the single bond concept. I think it was towards the end of the last class. When we say this, when we say that hydrogenation is occurring, we are talking about the fact that we are reducing this compound to its very nascent stage, and its nascent stage would mean for hydrocarbons, the nascent stage is usually their basic single bonded state. You will notice while we discuss these chemical reactions, their nomenclature is usually based on the molecule or the compound that you're adding. In this case, the addition of hydrogen molecule, we call that hydrogenation. And in fact, if you talk about this further, how does addition of hydrogen molecule, how does it improvise this? So let me clarify this further. I'll erase all of this here. How does it happen? Basically, if you have a double bonded structure and if you add hydrogen molecule to it, basically what it will do is it will attach itself. It will attach itself, the hydrogen molecule, and it will break this bond here. So that breakage of bond happens because hydrogen gets added, and as I said, it requires a lot of energy. Yes, it's a double bond, so it will require less energy than breaking a single bond, but it still requires energy. Therefore, production of ghee requires a lot of heat, energy. so on and so forth. There are other important compounds whose addition or removal provides their name. The next best example that we can come up with is H2O, water. Addition of H2O will be called hydration. Removal will be dehydration. When addition of water, when it results in, uh, there is another word we use, and this is very specific to the biochemical reactions we'll talk about, the concept of hydrolysis. Basically, addition of water, if it results in the breakage of a molecule, there we'll talk about how where polymers are broken down. What are polymers? We'll discuss that as well. Basically, if you add water, I'll write it down, and this will result in breaking them into its monomeric form. On the other hand, dehydration is where the monomers combine, or instead of poly you can say dimers or trimers as well. Monomers combine to form a dimer, but it is because of removal of water molecule. So here I'll use another color here. Here it is addition, here it is removal of water. So yes, technically you can call it hydration, dehydration. If addition of water breaks up a molecule, it is called hydrolysis. And this here, if removal of water condenses a molecule or condenses the compounds, it can be called literally condensation. As I said, there's a lot of verbiage you can use depending on what type of reaction you're talking about. So generally, addition of water is called hydration and removal of water dehydration. When water is used to break or combine various biomolecules, it can be called hydrolysis and condensation. We will make use of all of these terminologies. Please be aware. Another important, well, let's say element is nitrogen, and nitrogen based reactions form interesting life cycles. Nitrogen is the most abundant element in the atmosphere. Unfortunately, this abundance, so approximately 70%, around 70% of the atmospheric composition is nothing but nitrogen molecule. But we organisms, living organisms cannot directly, most living organisms cannot directly consume this nitrogen, so it is useless. Therefore, there are intermediary organisms that exist that are able to so-called fix this nitrogen, and it is called nitrogen fixation. I'm sure you've heard of it. Even if you haven't, we'll study this in complete life cycles. While I'm not interested in dealing with that life cycle right now, obviously, that is not the area of concern for us, area of discussion. What I'm talking about is the various addition of various nitrogen-based molecules and what we call them. So nitrogen could be in its basic form as ammonia. This is called, NH3 is called ammonia. Addition of ammonia is called ammonification, or when ammonia comes into the picture as a reactant, we call it ammonification. These are all terms you will have to deal with. If you already are aware that how they come across this word, you may be able to define it as well. Similarly, we have other nitrogen based compounds as well. You have NO2 nitrification, and so on and so forth. Then there are other oxides of nitrogen as well, nitrites, nitrates, so on and so forth. But as I said, wherever possible, I'll try to talk about this. For now, let's leave it at the fact that addition nitrogen is another element whose various compounds, their reactions are given specific names. And there are very specific living organisms that can partake in these reactions, so you should be aware of that as well. We will talk about those organisms wherever applicable. So on and so forth. There's quite a few. I've tried to explain a few basic compounds and their addition or removal, the name of the reaction, what we call the reaction if we talk about it. Further reactions, further name of the reactions will depend on the so-called functional group. But before I talk about the functional group, let's quickly talk about the concept of monomer. That is how we can discuss this further. Now, this is again continuation of the concept of carbon chemistry, or the carbon itself, the chemistry of carbon, that is the reason for it being the most important element on which life is based. As I've already stated, carbon has a unique property in which it's called catenation, according to which it can form long chains with itself. Now, another important rule of chemistry, and this is an ideal rule of chemistry, is the fact that whenever we denote carbon and whenever we notice that there is no other specific molecule attached to it, to complete its valency, we will always assume that hydrogen is attached to it. I repeat once again, when you notice that carbon has free valency, remember carbon can form 4 different bonds. If you notice that there is some vacant bonds, there is no specific mention, it is assumed that those will be with hydrogen. This is theoretically what we assume, and that's because, as I said, hydrocarbon is the most basic or list of organic compounds that exist. So this is an acceptable explanation to why when we are denoting carbon, we only notice carbon. We do not write H. It is given that H will exist. I repeat, it is always given that H exists. So in fact, the relationship between carbon and hydrogen, which we elevated to a series of chemicals called hydrocarbons, is one of the founding reasons for life. But let's not go into that here. What I'm trying to tell you is that this particular concept wherein carbon can form long chains with itself, it does not have to be a linear chain. Because there are other bonds available, carbon can also form these structures are also possible. Once again, you will be introduced to organic chemistry in high school, and in fact you will go on to study various aspects of it. But what I'm trying to tell you is, because carbon can connect with itself and it can form long chains, these do not have to be linear chains. It can be these haphazard, well, they're not usually haphazard, they can be these various angles, they can be formed, these chains. Not only this, they can form what is called a cycle as well, a cyclical structure as well. For example, carbon can connect with itself in a tetrahedron. This is the ideal shape of a tetrahedron. I repeat this once again, wherever you notice that carbon is either not attached to itself or to any other specific molecule, it is given that its valency will be completed by hydrogen. This, by the way, if the rest of the valencies are filled up by hydrogen, it is called cyclohexane. This particular molecule is called cyclohexane. So what I'm trying to tell you is that carbon does not have to necessarily connect with itself in a linear manner. It can connect with itself in these cyclical structures as well. There are very specific shapes it forms. There is something known as stereochemistry where you discuss these shapes, individual shapes and compound shapes as well. The reason I'm introducing these cyclical shapes is because when we deal with a lot of these biomolecules, it's because of the shapes that they can form, their use is known, their function becomes, they become activated, they can form other bonds, etc., etc. So it is because of these shapes that a lot of them, the shape is the reason why they are used by the living system. You should be aware of the shapes, or generally what is thought of as their shapes. As I've shown you, cyclohexane, it's called, exists as a tetrahedron. There is another interesting molecule that exists. It is also a tetrahedron. However, as I've said, if there are specific bonds and other molecules or elements attached to carbon or compounds attached to carbon, you have to mention them. For example, what if there are double bonds to this? There are double bonds at 3 places. That makes it C6H6. C6H6 is given a very specific name. It's called benzene. Once again, you will be introduced to this molecule in high school organic chemistry, and you'll be shown how instead of sticking to these double bonds, instead of sticking to these individual carbons, they are visible as, usually the benzene structure can also be denoted like this. What this circle in the middle means is the fact that these double bonds can actually move at any given time. You do not notice that they exist at one place. They are capable of basically isomerization. So on and so forth. You'll learn the various aspects of benzene as well. It's a very important molecule in terms of organic chemistry. But as I said, I'm introducing these concepts to you, so therefore it is important that we understand that. But most importantly, the next aspect of this class I would like to spend on the concept of functional groups. What are they? As I've already stated, carbon can either connect with itself or it can combine with other compounds. We have come across this list, this collection of various so-called functional groups, a collection of compounds. When they're connected to carbon, they provide the features, the characteristics, they impart the characteristics of that product. Basically, they are a group of compounds which will be the reason why these carbon long chains have unique properties. You will be given possibly towards the next towards the uh, class 12th, you read or study about these functional groups. You try to study the interrelation between these functional groups, particularly the reactions. Here I'm just going to introduce the basic ones. There's a long list obviously, but we are going to talk about a few basic ones. For example, if carbon connects, so wherever carbon connects, the long chain of carbon can be referred to as R. R would mean X number of carbons, and then you denote it with the functional group. This is ideally how you denote it. R is the X number of carbon chains, and then you denote the functional group. The first one we can talk about is OH, hydroxyl group. When it connects, it is called alcoholic group. I'm sure you're aware of this group. We are all aware of this group. Alcoholic group, when given the name, it's usually the ones ending with OL. Any chemical that ends with OL is usually an alcohol. It has an alcoholic functional group attached to it. For example, and so obviously how you denote it is ROH. That is how you denote it. The best example you can come up with in terms of alcohol is ethanol. Ethanol, which is liquor. All liquor that is consumed is various percentages or concentrations of the same compound, which is ethanol. As you notice, the OL at the end will hint to you, provide the hint to you the fact that it's an alcoholic group. There's a functional alcoholic group present here. Of course, before this, I should be talking about the concept of ethane, meth, eth, prop. These are basically names given to the number of carbon atoms. Since we're discussing this, let me quickly grab that as well. So when initially, of course, carbon chains can be long. Carbon chains can be long, but if it's only one carbon chain, if there's only one carbon, we can give it a we can denote it as meth. If there are two carbon in the chain, we can denote it as eth. If there are three carbon chains, we can denote it as prop. Four carbons will be denoted as but. And of course, as you move further, it does not have to be a linear chain, obviously. I'm talking about the total carbon strength in the structure. Therefore, ethanol would mean that there are, according to this, ethanol would mean that there are two carbons in this group, and there's a functional alcoholic group as well. The rest of it is filled up by hydrogen. So ethanol technically is CH3, CH2OH. Either you write it at this way, or you can write it as C2H5OH. It's one and the same thing. And once again, ethanol is an important byproduct. Byproduct of what? We'll study that in cellular respiration. Similar to alcohol, we have another group. So alcohol, where does it make a lot of sense? We'll initially, the various types of molecules that we discuss, what we call as biomolecules, we'll begin the discussion with what we call as carbohydrates. Carbohydrates will have a lot of OH groups in it. That is why we begin this discussion with alcohol. Similar to alcohol, we have another group called aldehyde, which already has a carbon attached to it. And the hint that you get that it is an aldehyde is when Al is attached to it. So even though the list is long, I'm going to give you some very basic ones. RCO, it is referred to as ketone. The word suggests ONE. Once again, the most common ketone you may have come across is acetone. Acetone is called as nail polish remover. So when you say eth, eth can also be referred to as acid. That is another common name given, although it is not the correct chemical name. Finally, we have another group called COOH. It is called carboxylic acid. You denote it as ic acid. The end, whenever it has ic acid, will be referred to as it has a functional. That is a hint to you that the functional group is carboxylic group. The most common example of carboxylic acid is acetic acid. Acetic acid or ethanoic acid is what we call as vinegar. So on and so forth. These are some very basic functional groups that exist. You should know how they end. For our scope of discussion is not to go into the actual chemistry of it. Our scope of discussion is to introduce you to these names. So where I want you to concentrate is how they end, these names, how they end. That's why I gave you these examples. These examples are to show you their name and how do you represent these names. Once you're aware of their representation, you may be able to make out what functional group you're talking about. While we're talking about names, you should understand that this is the suffix. It can also be prefix as well. It could also be prefix as well. What that means is these functional groups in a name, you can get to know whether these functional groups exist in a name or not by simply talking about their prefixes. For example, the most common prefix for alcohol is hydroxy or the hydroxyl group. Similarly, RCOH is the carboxyl group. Again, as I said, we are not interested in the chemistry of it. We are just going to talk about the names here. All of these will come into consideration in various molecules you study. Sometimes what happens is, and the reason I've chosen these two is because sometimes the same carbon chain can have multiple functional groups. For example, instead of if both the hydroxyl group can be connected to the same carbon atom, this is possible. Remember, carbon has valency of 4, which means it can form 4 bonds. Instead of forming those bonds with H, it can form these bonds with 2 functional groups. And again, the reason I'm stressing this is because the similar combination exists. So instead of COOH, there is another functional group here that I've not mentioned. Ideally, you don't study it. It is called NH3, nitrogen based group. It's called the amino group. Should probably mention it. The amino group. And this is very specific to what we talk about. If you talk about the amino group being attached, how do you call this? You can forget about this one. How do you call this particular molecule if the rest of it is H? How do you call this molecule? You have, let me pick out the names that could possibly. So you have a carboxylic acid and you have an amino group. If acid and amino group exists, can we call it amino acid? Some of you may remember, or most of you should be able to recollect this name. You have heard this word before. Basically, it is the building block of proteins, the basic unit that combines to form proteins. So amino acid is one unique place where you will notice multiple functional groups. Of course, there are a lot of combination of these functional groups that exist. We won't talk about all of them. This one, because we are talking directly about biomolecules, this will directly be helpful to us. Remember, the R could be anything. The R could be anything. What we're trying to say is that it could be X number of carbon chains or atoms. While we're talking about this particular structure, I should also bring to your notice the fact that This particular molecule or structure is also called a zwitterion. What is a zwitterion? To understand zwitterion, you can best take up the example of H2O. In the same molecule of H2O, remember I began the discussion in the last class, or maybe not began the discussion, but I talked about the fact that H2O as it exists, it is H plus and OH minus, or you can note down the H3O plus. So a Zwitter ion or a Zwitter ionic form is a molecule or a compound. It's a chemical basically which has both the positive cation and negative anion in the same molecule or compound. So a chemical in which both the cation and the anion exist in equilibrium or harmony equally, it is called a zwitterion. And just like water, amino acid is also an example. In amino acid, you notice that the entire definition of an acid is therefore that it can donate hydrogen. Therefore, in this case here, H can be donated. Let me change the color. H can be donated to the amine group, and what it can basically become is so what you notice here is the fact that this molecule or this compound, let's not call it a molecule, this chemical is capable of having two different charges of ions, cations and anions in the same molecule, in the same compound. Therefore, it's called a zwitterion. Remember, this R could have additional groups connected to it. This R does not necessarily have to be only carbon. It could have other positive and negative ions connected to it. So based on what is R, we could get a positively charged amino acid or a negatively charged amino acid. We will talk about amino acid further when we discuss proteins, but it is essential that since we are talking about, we're discussing or introducing chemistry, at least we introduce it appropriately, talking about almost all of the things. So the question that arises now that I was trying to keep it for the, well, I wanted to talk about this towards the end of the class. That's what we're approaching here, is what happens when we have these functional groups. These functional groups, when they exist individually and when they combine. Basically, what I'm talking about is when these functional groups, they exist as one unit. Let's say, because you're now aware of this structure called amino acid, let's take this as an example. What if amino acid exists on its own? A single compound of amino acid, it can combine with other amino acids. Let's call them AA. And this in itself, since these are all carbon chains, remember this R is carbon and even the carboxylic group is carbon, but we're talking about this R here. Since these are carbon chains, they can connect as these functional groups along with them as well. What I'm getting at is the fact that instead of only carbon or hydrocarbon connecting with each other, it could be carbon along with its functional group. Therefore, what we get, this long chain, is what we call a polymer. And usually the way you denote a polymer, so what is a polymer first of all? It is composed, it is a combination of monomers. You can make out that in this scenario, one amino acid will be the monomer and its combination will form a polymer, and combination means a long combination. So Individual monomeric units will combine together to form a polymeric unit. Usually, you denote a polymer as n number of times a monomer is repeated. This is how you denote a polymer. This n will tell you how many times it is combining either with itself or other monomers. Usually if it combines with itself, that is when you form this scheme. When we discuss biomolecules, you'll realize that most of these individual molecules do not stay individually. They actually combine and form very large structures to the point that they are visible not under the naked eye obviously, but under the microscope. Such large structures in biomolecules are studied separately, but we need to first discuss their monomeric forms. Only then can we talk about their polymeric forms, because at the end of the day, the polymer is nothing but a continuous combination of the monomer. And remember, I've already told you the fact that carbon does not have to combine. It can catenation does not mean that it is in a linear chain. These monomeric forms can take up very complicated shapes as well. So the monomer could combine in this manner as well. And this could be the basic scheme of polymerization. Under polymerization, we talk about a lot of commonly chemicals that you've already heard, such as cellulose, such as starch, and shockingly, even polyethylene, which is called polythene, plastic. Plastic is a polymer. One of the aspects of the polymer, so I'll erase this here. This is just to show you how complicated it can get. This is just an example here. One of the interesting aspects of this polymer is the fact that polymerization will yield a compound which is difficult to break down. Monomers, because they're individual units, they can be broken down easily. Polymers, because these units have combined together, they are difficult to break down. It is because they're difficult to break down, that is why most polymers are also, so when we deal with polymers, we deal with some salient features of these polymers, such as they are not soluble in acidic content, insoluble. Most monomers can dissolve in acidic content, but polymers are insoluble in acidic solvents. Their large structure, the large structure of the polymer also makes sense when we deal with protection, or how we call it, layerings. So polymers can comprise, most polymers will participate in protection and layering purposes as well. This large nature allows the protective layers to be formed, so on and so forth. So there's a lot of other features of polymers we'll discuss. What we'll do is we'll take up individual set of polymers. First we'll discuss the monomers. This is going to be the theme of study here. We're going to discuss the monomers first. We'll talk about the monomers, and then we'll move on to the polymers wherever possible. Remember, when dealing with biology, there are always exceptions. So when we deal with monomers and polymers, there is still an exception that exists, the concept of fat and lipids. They are technically not supposed to be polymers, but for various reasons, we'll discuss the reasons as well, they are considered, well, they're not technically polymers, but we'll be calling them, they are always associated with large molecules, so we'll give them appropriate terms. We talk about terms such as macromolecules. The word macromolecule in itself will suggest a large molecule. So the time being what it is, I shall not begin a new topic here. I would like to go back here. Let me see where I can go back. So once again, this list of functional groups is very limited that I've shown to you. As and when required, we'll introduce new functional groups as well. One of the other functional groups that I have not mentioned here is the salts, the chlorine, fluorine, bromine family. Those also can participate in the halogen group, halide group. They also participate in as a functional group. They have unique properties. And again, there is another particular functional group called the phosphate group. Technically, phosphate is inorganic in the sense that it is not technically carbon based, but phosphate group is intricately connected to a lot of biomolecules, so we will discuss those as well. So phosphate group is also another interesting one. Directly it does not act as a functional group. There's not a lot of functionality of phosphate individually, but there are molecules, there are compounds that will, there are structures that will combine with it, and its combination with those structures will form. So I'm talking about DNA. DNA particularly will make use of this functional group called phosphate. The list is long. Wherever required, you'll study this further. When we talk about the structures, I'm talking about this structure here. Benzene is one example. There are other ways you can come up with the structure. So particularly in carbohydrates, we look at the furan form and the pyranose form. So on and so forth. There are other structures you can talk about as well. Wherever possible, I'll try to show you these structures as well. At least be aware of this one, benzene. So this structure that you see, cyclohexane, remember it is not the same as benzene. The formula changes, C6H12, C6H6. And there are double bonds introduced. So I was trying to recap here what we've done. What we have tried to understand various chemical reactions that exist. Technically, you studied under the subject of chemistry that there are different types of chemical reactions. We won't be dealing with them directly, the concept of substitution, elimination, combustion. What we deal with is very specific molecules either being added or removed, and what name we've given particularly in biochemistry. You should be aware of them because in a lot of places we will introduce this concept: oxidation, reduction, hydrolysis, condensation, nitrification, ammonification, so on and so forth. So at least you should have an understanding of what is happening. So similarly, we have other reactions as well. Wherever possible, I'm trying to remember as many I could teach you. There is another group. It's not technically a functional group, but it is used significantly in biology. Methane is CH4. If one of the hydrogen is removed, it is called a methyl group. A methyl group participates in various biochemical reactions. Addition of the methyl group is called methylation. Addition of the methyl group is called methylation, and it is one of the markers. It is a so-called marker. We use this in biochemistry to observe various chemical reactions, and we use this for marking it. We'll discuss what the marker concept is, but you should be aware of the other existence of other compounds as well. The cyclical compound that I mentioned, benzene, that also exists as one of those compounds that can be added to the long carbon chain. And of course, I've mentioned halides as well. The concept of fluorine, chlorine, bromine, etc. They can be added as well. You will notice that wherever I talk about a chemical reaction, I am not talking about valency, because especially when we start dealing with, so these cyclical structures, these structures that are formed, we usually study them under the so-called aromatic organic chemistry or aromatic compounds. These these structures, when we form them, we call them aromatic compounds. Usually that is where we study it. So we've collected them together to study it separately. What I'm trying to tell you is that the fact that chemical reactions, when we deal with them in biochemistry, we are not looking at valency. It is understood that they will complete their valency, and one of the ways to complete the valency in organic chemistry is to attach hydrogen to whichever carbon chain is empty. It's not complete. That is a given in organic chemistry. By the end of today, we have tried to let's summarize the fact that we are talking about organic chemistry, its reactions, its basic functional groups. What do you call them? We are dealing with, at the end of the day, chemical reactions. That is what you should, by the next class we begin, you should be comfortable with these chemical reactions. If you're comfortable with these chemical reactions, or at least you're aware of the name, you can go ahead and continue the whatever discussion we are doing. Then you can recollect that we've already understood the name. Wherever possible, I'll try to recapitulate the names, re-explain them, but it's essential that you already have an understanding, so that you at least form a basis on which we study these topics further. The time being what it is, I'll end the class here. As I've said, we'll individually take up various molecules and we'll study. So I won't stress upon their structure. Yes, I'll show them to you wherever possible, the monomeric and the polymeric forms. I will not stress on the actual structures because, as I said, our studies have to do with the theoretical aspect of it. You should be aware of the name and what they look like. Yes, at some places the structure, how it looks like, becomes important. There we'll spend some time there as well. But most importantly, most of this chapter has to do with the nomenclature part of it, naming various chemicals. Any doubts or queries that you may have, please send it to me before the advent of next class. It is essential that we are all on the same page. These introductions were given so that we are now all aware of the general scheme of biochemistry. We can now proceed further and introduce various biomolecules to you. Literally, the name of the chapter is Biomolecules. Beyond that, this entire unit deals with things at the small level, at the microscopic level, and therefore beyond, after studying biomolecules, we'll talk about cell as well, the basic unit of life. So it is essential, before you talk about these large molecules, you understand the monomeric forms, the basis on which they're named, and then we'll collectively study how they interact. For now, I'll end the discussion, the lecture here. Those of you who are absent and checking this out as a recorded session, make sure you are comfortable with all the terms. Whatever doubts exist, fire them away. Ask me those doubts immediately. I may not be able to respond immediately, but at least you ask them. If I'll see how I can take up these doubts and queries. Probably we'll discuss this at the beginning of the next class. But make sure that whatever niggling doubts you have, they do not remain in the back of your mind, because then sadly the next part will not be understandable. This is all connected. With this, I'll take your leave here. Take care of yourselves. Goodbye and good night.